Welcome to this explainer, where we're going to unravel the mystery of mass. We'll be exploring the foundations of atoms, diving into isotopes, and learning how to totally effortlessly calculate relative atomic mass. So whether you're brushing up for a massive chemistry exam or you're just genuinely curious about the invisible building blocks of the universe, you are absolutely in the right place. Let's get right into it. Here's our roadmap for today. 1. Inside the atom. 2. What are isotopes? 3. Properties and real-world examples. 4. Calculating relative atomic mass. And finally, 5. Avoiding common exam mistakes.
We're kicking off our journey with a deceptively simple question. What rigid, golden rule actually determines the identity of an element like carbon? I mean, think about it. Out of all the tiny particles swirling around in the universe, what is the exact, unchangeable signature that makes carbon behave like carbon and, say, oxygen behave like oxygen?
Well, to answer that, let's jump right into section 1, inside the atom. Now, what's totally wild when you look at the architecture of an atom is that nearly all of its mass is crammed right into that tiny central nucleus, which holds the protons and the neutrons. You can see how the nucleus sits right at the core, tightly bound together like a dense little knot. Meanwhile, the electrons are just sort of zooming around on the outside. They take up most of the physical volume of the atom, for sure, but they contribute almost nothing to its actual weight. Let's break those particles down a bit further, because this is where the absolute golden rule of chemistry comes into play. If you check out the mass column, protons and neutrons both have a relative mass of 1, while an electron's mass is basically 0. I mean, it's about 1/2000th of a proton. But the really critical part here? The charge. The number of protons, which we call the atomic number, strictly defines the element. If an atom has 6 protons, it's carbon, period, end of story. If it has 3, it's lithium. The tiny orbiting electrons, on the other hand, well, they just balance out the positive protons to govern the overall charge of the atom. But here's the plot twist, and it brings us to section 2. What are isotopes? If all carbon atoms have exactly 6 protons, why do some carbon atoms weigh more than others? If the protons define the element, and the protons aren't changing, where exactly is this extra mass coming from? Enter the silent partner of the atom, the neutron. Neutrons have a mass of 1, exactly like protons, but they carry no electrical charge whatsoever. They're just kind of along for the ride. And it's their fluctuating numbers that create what we call isotopes. Because they don't change the charge, adding or removing a neutron doesn't change the element's identity at all. It literally just makes it heavier or lighter. This is a brilliant illustration right here. Carbon-13 is essentially just a rarer, slightly heavier sibling of carbon-12. Both of them have exactly 6 protons. That is non-negotiable for carbon. But carbon-12 has 6 neutrons, giving it a total mass number of 12. Carbon-13 has 7 neutrons, pushing its mass up to 13. See? They are both still carbon, they just vary by a single extra neutron. Okay, so they have different masses. But what's the so what? Let's explore section 3, properties and real-world examples, to see how these varying neutron counts actually affect things in the real world. This is a distinction you absolutely have to know. Because the electron count doesn't change across the isotopes of an element, they react chemically in the exact same way. If you drop them in acid or bond them with oxygen, you literally won't see a difference. But their physical properties do change. Because mass dictates things like density, boiling point, and melting point, those heavier isotopes are going to have slightly different physical thresholds. To really drive this home, let's look at the most famous isotopic family out there. Hydrogen. Normal hydrogen, which is called protium, has 1 proton and 0 neutrons. That makes up like 99.98% of all hydrogen, used in everyday stuff like plastics and fuel cells. But add just 1 neutron and you get deuterium, which is incredibly powerful and used in nuclear fusion. Add 2 neutrons, you get tritium, a super rare radioactive isotope used in thermonuclear weapons. It's crazy! Just looking at hydrogen, we see that adding 1 or 2 of those silent neutrons drastically scales its real-world applications, from a simple plastic bottle to a massive release of energy. All right, let's move on to section 4, calculating relative atomic mass. Let's see how all of this builds into the mathematical detective work of figuring out an element's overall mass. If you look at a periodic table, the mass numbers are almost never clean whole numbers. They've usually got decimals. And the reason for that is pretty simple. Any handful of a naturally occurring element contains a varying mix of its isotopes. So we have to calculate a weighted average based on how abundant each version is in nature. You can't just add the mass of the isotopes up and divide by the number of isotopes, because they don't exist in equal amounts. You've got to account for how common or how rare each one is. Now, instead of memorizing some intimidating formula with a bunch of confusing symbols, you could find the relative atomic mass by just breaking the math down into 3 really logical, super digestible steps. Step 1, take the mass of the first isotope and multiply it by its percentage abundance. Do that for every isotope the element has. Step 2, add all those resulting numbers together. And step 3, just divide by the total abundance. If you're working with percentages, that number is literally always going to be 100. Let's see this in action. Take copper. It's made of 69.2% copper 63 and 30.8% copper 65. By applying our steps, we land precisely on an average mass of 63.6. Think about the math. 69.2 times 63 plus 30.8 times 65. Add them up, divide by 100, and boom, 63.6. Notice how it leans closer to 63 than 65? That makes perfect sense, right? Because the copper 63 isotope is way more abundant. Just seeing these actual handwritten calculations proves that you can track your variables and solve for any unknown isotopic abundances just by methodically following those steps. You've got workflows here for nitrogen, copper, silicon, iron, lead. Notice how setting up a really clean algebraic equation allows you to work backwards, too? So if an exam gives you the final average mass but hides the abundance percentage of an isotope, no problem. You just set the abundance as x and the other as 100 minus x and solve it step by step. Keep your workings neat, and honestly, the math practically does itself. Now that we've got the math and the theory locked down, let's quickly hit Section 5, avoiding common exam mistakes. We want to build a sort of protective shield around your grades using insider secrets straight from examiner reports. These 3 errors cost students massive amounts of points every single year. First, confusing the numbers. Just remember, atomic number equals protons, mass number equals protons plus neutrons. Second, when you're asked for the electron configuration of an ion, you absolutely must adjust your electron counts. A neutral atom has equal protons and electrons, sure, but an ion has either lost or gained electrons to get its charge. And finally, in stoichiometry, always use the relative atomic mass from the periodic table, not the atomic number when calculating molar mass. So having mastered the mystery of atomic mass and learned exactly how to sidestep those common examiner traps, you are perfectly equipped to totally crush your next chemistry test. But as you look around today, ask yourself, what other invisible, silent variations are hiding in the objects you touch, the air you breathe, and the stars up above us? Keep questioning those fundamental building blocks of our world, and I will catch you in the next explainer.